Case Western Reserve University's Institute for the Science of Origins proudly presents the Origins Science Scholars Program. The Institute advances the scientific understanding and application of origins and evolution of human and natural systems. The Origins Science Scholars Lectures are presented with the assistance of Case Western Reserve University's Siegel Lifelong Learning Program, College of Arts and Sciences, and Media Vision.
Tonight we have Ken Singer. He's professor of physics at Case Western. He earned his bachelor's degree from Ohio State and his PhD from the University of Pennsylvania. His primary research areas are modern and nonlinear optics and condensed matter. And he's going to be speaking tonight on lighting the world of big data.
I'm going to talk on three subjects tonight. The first being the science of light. But since this is a series in quantum mechanics, I'm going to start with a couple definitions so that everybody's kind of on the same page on some of the analogies that I'm going to talk about today. So classical physics is the physics basically pre-20th century. It deals with things that happen at the human scale and above. And by human scale, I mean actually things that are accessible with light, which is about 10 to the minus 7 meters and larger, which is 10 to the minus 7 is about 1,000th of the diameter of a human hair. Quantum physics more recently is at the atomic scale and smaller, which is 10 to the minus 10 meters and smaller. So these are kind of usual definitions, but what I hope to do tonight is to kind of tell you that this isn't really the whole story. So light is so basic to us. It's, you know, a central part of our lives. And it seems mundane, but actually it's really cool, and I hope I convince you of that tonight. But it's something that people have thought about, you know, forever. And in antiquity, people were noticing things and trying to explain. So for example, on the left here is refraction, where light gets bent when it passes from one medium to the other. And what about the reflection of these trees in the lake? How does vision work? And even in antiquity, they made some devices like this ancient lens to manipulate light. And the Greeks made some progress in explaining light, but the real advances came in the Middle Ages, actually, in the 10th century, with a couple of Arab scholars, but Alhazen is by far the most important. He was a prolific scientist working in Egypt, and his 7-volume Book of Optics is considered one of the most important scientific books written. He basically was able to pretty much describe the way we know it today, how reflection works, how refraction works, how the eye works, how vision works, and so forth. And the way that he did this was he developed a method of testing hypotheses by rigorous observation. And that might sound familiar because that's the scientific method. He is actually the inventor of the scientific method. It was discussed in the optics book in the preface and revealed all this information about light. So one of the things he developed was a mechanical picture of how light behaves when it encounters an interface between two materials. And so let me just kind of walk you through one of these just to get some definitions here and some understanding of how light propagates. So this is a mechanical picture of light. There are two materials. On the left, the white material could be air, and on the right is a denser material, could be water or glass. And the important quantity that describes how light propagates in material is the index of refraction, which I denote here by N1 and N2, because the indices are different in these two media. And in fact, N2 is greater than N1 in this case. So the index of refraction actually describes the velocity of light in the material and is given by essentially an inverse relationship proportional to c, which is the speed of light in vacuum, which is a fundamental constant of nature. So the refractive index also describes how the light will, refract at the interface. So in this case, a ray comes in incident at an angle theta 1 to the perpendicular to the interface, and then gets refracted and bent toward that perpendicular line. And that happens because N2 is greater than N1. So this mechanical picture basically sat around for a while, and it was taken up by two scientists in Europe in the 13th century. This was Grotest and Bacon. And Alhazen's work was translated into Latin, and they took up the study of optics, but more importantly, Bacon is actually credited as being the first European scientist because he applied many of the methods of Alhazen. But this mechanical picture of light was very naturally picked up by Newton because he was the person who essentially invented classical mechanics, which is the motion of material bodies. So his idea of light was that it was made up of particles. But about the same time, Grimaldi and Hooke noticed that when light went past the edge of an obstacle, it would bend a little bit. And you can see this in this photograph here. And Huygens was able to explain this as a phenomena of a wave. And they had been studying water waves, and this basically is what he thought. And there was this tension for actually several decades on is light particle or is it a wave? And we thought this was settled in the 1900s when Thomas Young did his experiment. In this experiment, there's a light wave that's incident on a screen that has two slits in it. And when the light goes through the two slits, it generates what are called two coherent waves, which will add in a particular way. And this particular way creates bands on a screen located some distance from the slit. And these bright and dark bands are a very unmistakable signature of a wave. So after this experiment, everybody was convinced light was a wave until this guy came along. And I didn't put his name because probably you know who he is. And this happened, this was one of the major results that was the invention of quantum mechanics. That is the photoelectric effect. This is the one thing actually that Einstein got the Nobel Prize for. And this basically is the idea that that light is made up of particles called photons, which are electromagnetic quanta. And the way that this was proved is through the photoelectric effect, where a single photon knocks a single electron out of a piece of metal. So now we have two unequivocal demonstrations that light is particle and light is wave. So the modern view is to say, yes, it's both. This is the wave-particle duality, and it's central to quantum mechanics, and actually it applies not only to light but to matter and all quantum systems. They can look either as waves or particles depending on the situation. And for light, classical is the electromagnetic wave, and quantum is the photon. The classical picture is most useful when there are many photons, like in the room, the human scale, classical. So I've mentioned electromagnetism. Let's talk about that a little bit. That's one of the fundamental four forces of nature, and their gravity, electromagnetism, strong and weak, which are at different scales. Electromagnetism is the one that's actually at the human scale. It's what binds the electrons to the nucleus in the atoms and responsible for pretty much everything in our everyday life. And gravity, of course, is on long scales, and the strong force holds the protons and neutrons together in the nucleus. Electromagnetism comes about from charged particles. The red particle, for example, might be a proton plus charge. The minus might be an electron. They're attracted. These are the lines of force. The lines of force between the two charges, and if they were the same, the force would be repulsive. So these are charges that aren't moving. When they're moving at a constant speed, like wending its way through this coil here, then a magnetic force is generated, shown by those lines, and when they're accelerated, electromagnetic waves are given off and energy with it. And the modern view is that charged particles interact by exchanging photons. So the electromagnetic wave is pictured here. And this is basically what James Clerk Maxwell came up with at late 19th century. And the wave is an electric field or an electric force field given in red here that's oscillating in time up and down in that plane that it's in. A magnetic field is oscillating in the plane that's perpendicular to it, and both of these are progressing in space, propagating to the right. The distance between the peaks is the wavelength. The frequency it's oscillating is the frequency, and the product of those is our fundamental constant c, the speed of light in vacuum. And then the energy is proportional to the frequency. N is the number of photons, and h is a fundamental constant associated with quantum mechanics. So electromagnetic waves can come in all wavelengths, and what's shown here is the spectrum from the very long wavelengths on the left, radio waves, to the very short ones on the right, gamma rays. And light, visible light, occupies this narrow spectrum in the middle between 400 and 700 billionths of a meter wavelength. And the color that we perceive has to do with the wavelength and frequency of light. So quantum mechanics, I'm going to change gears here a little bit. Quantum mechanics is making something that happens in discrete bits, like the dripping of the water from this faucet, versus the classical, which is continuous, which is this water pouring out of the faucet. And that's what we're going to talk about now, and talk about quantum matter. So in the pre-quantum view, an atom was a nucleus, a little particle in the middle with electrons going around them like planets around the sun. Mostly empty space. The electrons are very far away. But the problem is those electrons are accelerating, meaning they're giving off radiation, which reduces their own energy, and it would collapse into the nucleus. So that was kind of the dilemma faced by physics at the late 19th century. And the answer to that was quantum mechanics, where the electron is not a particle, but a cloud of probability, shown on the right, where it's the probability of finding the electron in the atom. So that's the quantum view, that matter is a probability wave, and then the energy associated with the atom is quantized, and I'll describe that in a few minutes. Any questions?
My question concerns that illustration in the upper left-hand corner. You have light moving into a medium and it bends. What causes is maybe a change in the velocity of light caused by the density of what it's entering is the item that makes it bend?
Yeah, and it actually, because the speed changes, the momentum changes, and you have to conserve momentum. That's what I meant. It's a mechanical picture of light.
Thank you for joining us. You have been watching Dr. Ken Singer discussing the modern understanding of the dual wave and particle natures of light. For more information on the Origin Science Scholars Program, please visit the Institute's website at origins.case.edu. In the next part of the talk, Dr. Singer will discuss how quantum mechanics affects the way waves travel through matter. Now, back to the talk.
I want to go on with quantum mechanics now, but bring light into it. And where we're going to end up is artificial quantum mechanics, things that people can make that are quantum, even though they're not 10 to the minus 10 meters long. So this comes about, it's really summarized in this table. So what I said in the last segment was that in the classical view, matter was a particle. It was that nucleus with the electron spinning around it. Okay, those are particles. And as I finished, in the quantum view, an electron is a cloud of probability. It's a wave. Light, on the other hand, as I said earlier, in the classical view is an electromagnetic wave, but in the quantum view is a particle. Okay, so kind of these pictures switch places, and that's what we're going to take advantage of to make new quantum materials in the laboratory without having to work at the atomic level, but rather work with the same types of methods that are used to make computer chips. What is common to both of these pictures is that both in light and matter, energy is quantized in quantum mechanics, and most important is, for what I'm trying to get at, is that light waves and matter waves are both waves, and they actually behave in a very similar way. So you can make a light wave act in a way that's analogous to a matter wave. So let's start talking about that. So I showed you this picture before, which is a traveling wave. That's like the light in this room. It's moving in space. And as I said, it's vibrating as it goes along. But that's not the only way that you can have a wave. Now, of course, electron waves can also travel through space, not in air, but in a vacuum tube. In fact, in a television, that's exactly what happens, and it's a traveling wave. But quantum mechanics is based mostly on bound waves. So I'm illustrating that here with, say, a guitar string. You pluck the string and you set up what's called a standing wave, which has what's called an antinode in the middle and two nodes on the end, because that's where the string is fixed. And if you squint at this, you can see that that form is a half of a wavelength. So the length of the string is L, and a half a wavelength occupies that length. And as you know, when you pluck a string, the fundamental wave has the lowest frequency, the lowest pitch. If you pluck it harder, you start to get harmonics, which vibrate at higher pitches, higher frequencies, and the wavelength will divide into 2, 3, 4, 5, etc. So what you see as you go down here, that there are these modes that are F, 2F, 3F. And I've already said that the energy is proportional to the frequency. So now we can arrange the energy here into a set of discrete states, N1, 2, 3, 4. This is quantum mechanics. We've quantized the energy of a vibrating string. So it's not just an atom, it's something that you can do at home, actually. So this is quantized energy, and this is exactly what happens in matter. And that is the electron and the neutron are bound together by the electrical force. And because of that, the waves associate them are restricted in space, and you get these modes, which are shown here in this diagram as the quantum states of the electron in the atom, n equals 1, 2, 3. In this case, they're not equally spaced because of the details of the attractive force between the nucleus and the electrons. So this is quantum matter. It's a little more complicated than that, and I want to go into this because this is how you explain where light comes from. Pretty much all the light that we ever see comes about because of what's on this slide. So as you can see, illustrated on the left is the ground electronic state, the first electronic state, and the second, but they're actually bundles of states because what I told before was a single atom, but atoms are almost always bound together with other ones, as shown in the upper right, and you can get rotations and vibrations, and those also lead to quantum states in this atomic world. And so you get these families of states, and the way light comes about is the electrons like to stay in the lowest states, and many of these upper states are unoccupied in these materials. And if you add energy to the atom, it can kick these electrons into the higher states. So, for example, from the ground to the first excited state. But once they're there, they like to go back down. And as soon as they go back down, they're losing energy that they originally gained, and they give off a photon of the exactly amount the energy they lost. So if you heat some metal up, what happens is you start adding energy into all these atoms, and they start to give off light, and it starts to glow, and the color of the light will depend on the temperature of the metal. So this is where light comes from, all the light. And I'd like to take this a little further, is that the proof of quantum mechanics is all around you. Just look at your sleeve. What color is it? Okay? Most color can only be explained by quantum mechanics. So this is what it is, the transition between quantized molecular states. So in this coat this woman's wearing, it's dyed red. So if we take this dye and dissolve it in a solvent and shine white light through it, what we find is that most of the light between 400 and 600 nanometers is absorbed by this quantum state, which is this peak. This peak has a width because of those vibrational and rotational bands and other broadening mechanisms, but light in that range is absorbed. So now we put that dye in the coat, you shine white light on it, all those colors are absorbed by the dye, and the light that isn't absorbed is reflected, which is greater than 600 nanometers, and guess what color that is? It's red. Okay, so this is proof of quantum mechanics in your everyday life. So now I'd like to turn into the subject of human-made quantum mechanics. And kind of the easiest one is just taking two mirrors, like in the barber shop, and have them pointing at each other. And if they're not perfect mirrors, then you can leak some light in from the outside on the bottom left, and it'll bounce around. And because of the mirrors kind of hold the wave at the edges, they form standing wave modes shown in the middle. And those modes are very much like the string modes that I showed before. And on the right at the bottom are the energies associated with those modes. So I've now made a quantum system of light. And an example where this use is actually a laser. So a laser consists of two reflectors, one of them partial so that the light can get out. And inside the laser is a medium that has a lot of has important quantum states that can be pumped in a specific way. So you input energy, which you can do with light or electricity, or there are a number of ways, collisions, whatever. And what it does is it pumps those electrons up, just like I said before. But because they're in a mirror, they get very concentrated and energized. And what happens is you get a lot of them in this upper state, and they all hold hands and jump off at the same time. And this is called stimulated emission, which is what lasing is. And you get this very well-defined monochromatic beam of light coming out. You see green, red, and purple. And that involves these modes of this cavity with a material inside. So let me give another example, which is kind of a more, even more recent topic, and that is I'm going to start with the material version of this, which has been well known for a very long time, which are crystals. Crystals are ordered arrays of atoms. In this case, it's silicon, and what you see in the middle is the unit cell of the silicon. And it itself has a number of atoms, and the scale of separation between these is on the order of 10 to the minus 10th meters, okay? And in a silicon crystal, this pattern in this cube is periodically repeated, many, many times to create this well-ordered crystal. And in fact, silicon crystals are the basis of modern computer technology. So you can do the same thing with light. And these are called photonic crystals. Instead of periodic arrangement of atoms, it's a periodic arrangement of materials having different refractive indices. So the red and the yellow are materials with different refractive index. They're periodic. They can go on, for long distances. And shown here are patterns that are one-dimensional on the left, two-dimensional in the center, and three-dimensional on the right. And the length scale of these now, instead of being 10 to the minus 10 meters, is the scale of a quarter wavelength of light, which is hundreds of nanometers. And this is very typical to be fabricated using the methods that computer chips are made by. And in fact, in the lower part of this figure, you see a three-dimensional photonic crystal made this way. So what happens is these crystals can do the same thing that photonic crystals can do the same thing that material crystals are. And I'll show an example here with a one-dimensional photonic crystal. We have two materials of alternating refractive index whose thickness is about a quarter wave. What happens when you shine light into it, because the indices are different, you get some amount of reflection at each interface. And so you get this very complicated pattern of light traveling to the right and left and all these elements of this array. But when it all works itself out, you get this interesting pattern shown at the bottom, which is exactly the same thing that you see in a semiconductor crystal, and in fact is responsible for the mechanism that it works on in a computer chip. So it's shown here. This is the transmission on the bottom left, is the transmission of light through this structure. at different wavelengths. And what you see in a band approximately from 500 to 650 nanometers that no light gets through. This is called the stop band. And in a material semiconductor, it's called a band gap. And this can be very useful. On the right is just the reflection. So the light that isn't transmitted gets reflected. So this can be very useful. And I'll show you something from my own laboratory, which is this. Okay, this is not sandwich wrap. Okay, it's a laser. And it's actually made the way sandwich wrap is made, but it's a laser. And it's basically, I think this one is 32 layers. So even though it looks very thin, there are 32 layers, each layer about 250 billionths of a meter thick. And there's alternating layers. Say, for example, the red is one polymer, and in that polymer is a dye that can be made to laze. And then the other polymer has a different index of refraction. So it is this photonic crystal, the light's bouncing back and forth, but now there's this laser gain medium inside. And in the lower part of this slide, what you see is at the edges of the stop band, you see these peaks. And these peaks relate to the delay of light at those wavelengths. And what it really means is that at those band edges, light slows down a lot, okay? And because it slows down, you can get a lot of gain in your laser, and those are the wavelengths that the laser lasers at. So in the upper right is actually this stuff, lasing. So we have this film, and you shine a laser through it at an oblique angle, which here is this little green pump laser. And then the bright yellow laser that's coming out perpendicular to the film is the laser. And we can change the color by picking which dye we put in here and adjusting the thicknesses of these layers. So this is one example from my lab.
Does the light itself, do the photons actually slow down, or are they simply zigzagging through the medium, like a running back on a football field?
They're zigzagging.
Okay, so the photon never actually...
Right, because the index of refraction is what determines the speed of light in there, but they slow down because they're circulating a lot. Yes, good question. Thank you.
Are there ways other than another laser to pump it? Or what are the characteristics that the pump has to have?
This particular laser is pumped with light. It could be a laser, but it could be a light-emitting diode. We haven't demonstrated that yet, but that's a possibility. But this one can only be pumped with light. Other lasers, depending, can be pumped in other ways. Yeah, so this is useful because you can select different colors that aren't accessible with other lasers.
We hope you've been enjoying the Origin Science Scholars Program with Dr. Ken Singer. Dr. Singer is Ambrose Swayze Professor of Physics at Case Western Reserve University and founder, Executive Chair of Board, and Chief Innovation Officer of Folio Photonics Inc. In the second part of our talk, we learned about photonic crystals, periodic structures designed and built to affect the motion of particles of light, called photons, in much the same way that ordinary crystals affect the motion of electrons in solids. In our final segment, Dr. Singer will tell us about the technology he and colleagues developed to use photonic crystals to store large amounts of digital data. Now, back to our talk.
I'm going to go on a little bit with what I've been talking and then kind of turn my attention to, the subject of the title of the talk, which is how light enters into the world of big data and basically applications of light besides the crystal. So this is the laser, rather. So this is the laser, but this is a photonic crystal is one of a class of what is now known as photonic metamaterials. And these are materials that you can design that do really weird things. And you can make them using various techniques like photolithography has made computer chips. So in the upper left is a structure that has a negative refractive index, which you can see in those glasses bends the light in a really bizarre way. And this actually allows you to make a lens that focuses light to a very, very small spot below the usual limit for focusing light with a lens. And the same in the upper right is a different kind of lens. It's a metal lens that can be used to do all sorts of strange things. But actually, these are being investigated because they're very flat lenses, and you could essentially make a camera in something, you know, a millimeter thick. So someday our cell phones might have lenses like this as they get very thin. And then the coolest thing, of course, is the cloaking device in the lower left, which the picture of the hand there, that is totally phony. Nobody's done that, but it illustrates the idea is that the light from behind goes around in such a way that the object it goes around is invisible. And it's been done at a very modest scale, and you know, it seems to work. So now I want to talk about big data, and you can't talk about big data without talking about the internet. So the internet is optical fiber. And actually I worked at Bell Labs in the 80s and I worked on this, in fact. I worked when optical fiber was being deployed in the telecommunications network. And in the early 80s, it was long haul across the country. And then the late 80s, when I was about to come to Case, it was transcontinental. And in the bottom is shown maps now of the major cable lines. And this is really the backbone of the internet. All these optical fibers all over the world and the country. And all of them involve these fiber optic cables that are pictured in the upper right-hand corner. So these, in fact, optical fibers are another example of an artificial quantum system. It's a system where the light is bound and forms modes. So in this case, it's a little different. So to understand it, let's think about the pool at the lower left. So now the light is coming from a material with a high index and going into air, which has a lower index. So this is the opposite of what I showed at the beginning. So now when the light comes out of the water, it bends away from the normal. So that means in the ray marked B there's a certain angle where the light that's coming out gets refracted along the surface, and if you come at it even steeper or a shallower angle, the light gets reflected. And this is called total internal reflection. And this is really the basis of an optical fiber. But in the optical fiber, you have a core. It's made entirely of two different glasses. In the core is a higher index glass surrounded by a cladding of a lower index. And the light gets reflected inside. But the length scale of the core is on the wavelength of light, very near that. And so what you want in optical fiber and what's in the network is what's called a single mode fiber. So the core is so small that only one mode can operate in the fiber. And when you have that, you can push a tremendous amount of data through the fiber, which is why there was so much interest in doing that. It's many orders of magnitude more than you can stuff into an electrical connection. So in this case, the light is confined in 2 dimensions, in the direction perpendicular to the length of the fiber, and it's actually propagating in the fiber. But the use of this, of course, is you can control where the light goes. It'll bend around corners, and that's basically, you know, how you get these cables that really just look like electrical cables, but they're carrying light. So that's basically what's carrying all the data in the internet, is these optical fibers. And we'd never be able to have the internet like it is without them, because the capacity of data they can carry is enormous. And the other component is a semiconductor laser in the internet, and this is basically a miniature laser. This one is pumped with an electrical current through 2 semiconductors. So the red and the blue are 2 different semiconductors, one that attracts electrons, one that repels them. And when you pass a current through them, you excite the electrons, and then they laze coming out of the sides. And in this case, the cavity, the mirrors are formed just by the edges of the semiconductor crystal, and in the package it'll come out the little hole you see. So this is another, this is actually what I worked at Bell Labs, was trying to figure out, we have all this data coming down this optical fiber, but you have to switch it. And the only way to switch it is in a computing machine, which is electronic. So you would have to change the data to electronic, and then you lose all the advantage of the high capacity of the fiber. So we're trying to figure out how do you get around that, and this is an example, what's called an electro-optic switch. So these green lines here are waveguides. Think of them as optical fibers, but they're etched in the surface of a silicon wafer, for example. And when these waveguides get close together in the middle, because light is a wave, it actually, if the length is chosen exactly right, it's designed, the light will hop from, say, the top waveguide to the bottom one, and then come out the bottom right. And this has to do, what's important for this to happen is the index of refraction. Well, if you have the index of refraction dependent on the voltage that you apply between the 2 yellow electrodes, then you can change the propagation of light in these waveguides and cause them not to jump from one to the other. And so you put the light at the left top and it comes out at the right top. So this, in fact, is a 2x2 switch and can be used to switch phone calls, but maintain the data in the form of light so that you take advantage of the high capacity of the fibers. The other thing that I'm working on now, and I worked on a little bit there, is actually making an optical computer. And the idea here is we're back to our optical cavity here, the 2 mirrors, which have these modes, and on the right are the energy of the modes. But instead, if we fill this cavity with a material whose index of refraction depends on the intensity of the light in the cavity, then as you turn up the intensity, the index of refraction changes and these modes will move around a little bit. And you can use this to make an optical switch. So in the lower right, you can see as you, along the horizontal axis, you increase the intensity. Some intensity it jumps up because it jumped into a mode or out of a mode and becomes a high output. And then as it comes down, it goes back down. And this is an optical logic gate, actually, and could be the basis of a computer that uses light instead of electricity. But, and yet something even more recent, in fact, incredibly recent, is this report, which is basically making a quantum computer with light. So this really takes the analogy that I've been talking to its limit. Light is a wave. matter is a wave. It turns out that the fundamental operation of a quantum computer that most people are trying to make with matter can be done with a light wave. And this chip actually is a 2-qubit quantum computer that's fully reprogrammable. And so this is kind of something that actually in the community is being called a classical quantum computer, and it's kind of easier to use. This is actually a chip about the size of a quarter, and you know, it's not big, and we don't know yet if it's scalable, but if it is, it could be a quantum computing technology. So now I'm going to move, and my last topic is about my company. Actually, it's a spin-off company from Case Western, and it involves optical data storage. And the object on the upper left should look familiar to you. It's an optical disc. And at first they were CDs with a low capacity, you know, less than a gigabyte. Then we had DVDs with a higher capacity, so now instead of just music, you can store a movie. Then we had Blu-ray, which could store a high-definition movie. And all of these were kind of used in personal computing as well. But for one reason or another, these markets are starting to fade away. So we're interested in a different market, which is data archiving. And in this case, the capacity of the disk has to be on steroids. It has to be much larger than anything now. And the data archiving problem is actually becoming a very important problem. This graph is the growth of data. You know, in the mid-next decade, there'll be 100 zettabytes of data. Zettabyte is 1 billion trillion, okay? It's so much you can't even conceive of how much data that is. And 60 to 80% of data becomes archival eventually. So this is going to be a huge issue. And you know, a lot of this data has to be kept a long time, like in medicine, the movie industry, surveillance videos, so forth. So right now, this archiving is mostly done on hard drives, like on your computer, and shown in the upper right is a data center. This is actually one of the hundreds of thousands of data centers that comprise the cloud. The cloud isn't fluffy. The cloud is actually incredibly dirty and energy consumptive, use so much energy that they have to locate them next to hydroelectric dams. They're now starting to put in the Arctic so that they can just open the window to cool them. And you know, they're tremendous consumers of energy. On the left is actually a new product that several Asian companies are coming out with, and these are giant jukeboxes of optical discs. And the advantage of optical discs is they can be stored in warmer temperatures and could solve this environmental problem. And so my company, Folio Photonics, is aimed at developing a high-capacity disk. And the way we do it is none other than this film that almost looks like the other one. This is a 16-layer film with a fluorescent dye in it, just like the laser. But the data is stored using the fluorescence. So we use a high-intensity laser to bleach the fluorescence, and the bleached areas are the data, and the unbleached data are the other areas. And just to remind you, fluorescence is, what we do is we use a Blu-ray laser to excite the dye, which sends the electron to the upper state, then it relaxes to the lower state and fluoresces. And we basically have a 16 to 32 layer it's Blu-ray disc which will be at the scale of a terabyte, which is now a similar scale. The important thing is that the cost to making a disk doesn't depend much on the capacity of the disk. So increasing the capacity lowers the cost. So, you know, this should be a low-cost method because of the large capacity. And in addition, the data lasts much longer on an optical disk than in magnetic media, which also lowers the cost. So this is just a little movie showing a microscope scanning down from layer to layer. So on the right is a cross-section of this, and the microscope's going down. Those little pictures are a few microns on a size, about a millionth of a meter on a side. And basically, I'm not going to wait to get to the bottom, but there are 23 layers that we've written in. So this is the basis of the technology that we're doing. And now I'll tell you about how we make these essentially quantum systems using the method of making ketchup bottles.
Now let's look at how our films are produced. Polymer is added to two hoppers, which melt and then pump that material into a feed block. The feed block forms a bilayer flow, which then passes into the layer multipliers. The heart of the co-extrusion process is the layer multiplication stage. The bilayer flow enters a series of multiplier dies, which split the flow vertically and then recombine the two flows, resulting in a doubling of the number of layers. Any number of multipliers can be used, producing a few to thousands of layers. The flow exits the extruder through a final die which spreads and thins the film. Here we see a transparent multi-layer film being produced. The final product is taken up on a roll.
That machine can make enough material in an hour to make 10,000 disks. It's a very low-cost manufacturing process. Combined with the high capacity and long life, we're going to take over the archiving industry. So, and actually this company was a spin-out of a National Science Foundation center at Case Western. And we've been in business about 5 years, still building prototypes. That's it, and thank you for your attention.
Can the discs be reused or edited?
No, they're right once, and that's actually good and important because they are intrinsically more stable that way, and they're going to be so inexpensive that you wouldn't bother to rewrite them.
You mentioned that the current system of storage on spinning hard drives is energy intensive and that the cloud is not cool and fluffy, it's actually hot and hard. So how much is all this cloud computing contributing to global warming?
I believe it's 10% of energy consumption. It's a lot. And it's going to get worse because of blockchain. If blockchain catches on, because in blockchain, if you don't know what blockchain is, it's the basis of Bitcoin, but more important, it's a very secure way of keeping transactions. And so it's potentially could be used in the financial system, any kind of transaction, supply chains. It's already used in supply chains. The issue with blockchain is it makes thousands of copies of everything and distributes it to different computers. So you can imagine what it's going to do to the data storage.
The Origin Science Scholars Lectures are presented by Case Western Reserve University's Institute for the Science of Origins, with the assistance of the Siegel Lifelong Learning Program, the College of Arts and Sciences, and MediaVision. For more information on the Origin Science Scholars Program, including a full video archive, please visit the Institute's website at origins.case.edu.